And the way that we can actually do this is we can write what is called the electron configuration. So what I want you to do is I want you to write this underneath of the actual answer. So when it comes to helium, another way in which we can show the exact same, once again, information, is just simply write what's called the electron configuration. And for the electron configuration, we're going to first start off by listing the sublevels. So that's where the electron is located in the 1s. And then we have a grand total of 2 electrons in that sublevel. So we just put it as a superscript sitting right here. And then we just simply say, hey, the electron configuration for helium happens to be 1s2. And once again, this conveys the exact same information as the orbital diagram, and it's a little bit more condensed in this case. For number 2 is done spot on, beautifully. Everything is put in there correctly. So for number 2, if we wanted to write the electron configuration for magnesium and kind of have this thing a little bit more condensed, then what we do is write down 1s2, 2s2, 2p, and in the 2p sublevel, we got a grand total of 6 electrons, so we'll put a 6 right here. And then we'll go 3s2. And once again, it conveys the same information. We start from lowest in energy as far as the electrons, and go to the highest in energy electrons sitting here. For number 3, this is done perfectly as well. So the electron configuration for boron happens to be 1s2, 2s2, 2p1. For fluorine, fluorine looks perfect. So if we write the electron configuration for fluorine based upon its orbital diagram, then we got something that looks like this: 1s2, 2s2, 2p, and then if we count the number of electrons, you got a grand total of 5 electrons sitting there. For the next one, number 5. Number 5 looks like that's sodium. And for sodium, that orbital diagram is perfect. If we write the electron configuration for sodium, it's 1s2, 2s2, 2p6, 3s1. And then for argon, argon's orbital diagram is perfect. Man, this class is on it today. So let's see what we got here. Electron configuration, 1s2, 2s2, 2p6, 3s2, 3p, in this case. What do we got here? 3p6. There we go. The last one that we have here is we've got calcium, and we are on a roll here. So for calcium, I'm going to write its electron configuration. So its electron configuration is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2.
Wait, what? 3d6? Or 3d2?
Why is it not 3D?
Oh, you're right. It's 4s2.
Wait, no.
Now, the question you're asking is, wait a second, Mr. Hurlston, what are you talking about? It's 4s2. It's clearly, according to the orbital diagram, the next sublevel that the electron should actually go in is going to be the 3D. Now, one of the things that we talked about a little bit early in the chapter, and I told you it was going to have some ramifications here, is we talked about the fact that when it came to the actual energy levels, unlike the rungs of a ladder that are evenly spaced, when it comes to the energy levels, they have a tendency of getting closer and closer. And if you think about it, if they're getting closer and closer, but yet they have more sublevels in this case, too far here, what's going to start happening is the sublevels are going to start to actually overlap. And what's going to happen here is because these things are getting closer and closer together, the n equals 4 sublevel, our energy level has its sublevel that dips down here and it goes 4s, which actually becomes lower than the 3Ds. And the electrons, like, once again, I remember the all principle says I want to exist in the lowest possible energy level. So I'm going to go right here and here. Wait a second. I think I can read your mind, Charlotte. I believe I can. I'm not 100% guaranteed, but we're going to see here. The question that you probably are asking, how in the world am I supposed to know this? How am I supposed to figure this thing out?
Yeah.
Also, if you think about it, there's another question you should be asking as well. The other question that you should be asking is this. What is the purpose of this electron configuration? Yeah, it is a condensed form. But if I have to write this and then write this, then it's a waste of my time in this case. So one of the things I'm going to do is I'm going to show you how you can figure out where the overlapping is taking place. I'm going to also show you how you can write the electron configuration without using the orbital diagram. And that's what we're going to look at today. We're going to look at trying to figure this thing out. And then by the end of the day, I can give you any elements with any overlaps. And you can recreate what the orbital diagram is going to look like. So what we're going to do here is we're going to first start off by you either having a blank piece of paper or a blank page of notability. Oh man, look at this board. This thing is not erasing that well at all. Oh, that's awful. It's like the worst erase ever. All right. Would anybody happen to have some WD-40 on them?
Yeah.
You just pull it out like, hey, I've got WD-40. Because WD-40 would actually correct this issue I'm having with the board. If you could actually look at the board like really, really, really closely, microscopically, what you would see is there's little indentions, little crevices in the board here. And what's happening, the reason why I'm having a hard time actually erasing it, is the ink is getting in those little pores, and as I go on the surface, I can't get in the pores there. So a lot of times when it comes to these blackboards, if they ever start doing this thing, a lot of times what I'll do is take WD-40, spray it on the board, and I'll wipe all the WD-40 off. But what it does is it now seeps into those holes. And as you write, the actual ink won't penetrate into the oil because it's like, hey, it's like water and oil, the two don't mix. And then you don't have this issue that's actually going on here. Just pointing it out. All right, here we go. So what you're going to do is you're going to draw a picture that looks like the following here. All right. And once again, try your best. Once again, I know you might not necessarily have the same artistic skills that I have, but it's okay. Just try your best. Here we go.
Boat.
A boat.
Oh, no, it's a periodic
Castle.
table. It's a periodic table.
Thank you. It took you that long to figure this thing out.
Yeah.
I mean, that's obvious.
No, it's really not.
Yeah, it really is. Are you
gonna
assaulting
be
my
honest here,
artistic
guys.
skills here?
Of course not.
Of course not. All right. Now, one of the things to point out is the periodic table is an amazing thing that we have in chemistry. If you remember, the person responsible for discovering the periodic table was Dmitri Mendeleev. And Dmitri Mendeleev didn't even understand all the things that he figured out by organizing his periodic table. Because one thing you gotta think about is the quantum mechanical model. Dmitri Mendeleev knew absolutely nothing about this particular model. That's, once again, before his time. But one of the things you're gonna notice is that the quantum mechanical model seems to go right along with this periodic table. So watch how this is gonna play out. When it comes to the periodic table, it's actually broken into 4 boxes here. And if you think about the different types of sublevels that we have how many different types of sublevels? We got 4, exactly. We've got the S sublevel, which we're gonna know this is actually being the S block of the periodic table. We've got the P sublevel. This is going to be known as the P block of the periodic table. We've got the D block of the periodic table, and then we have the F block of the periodic table. Now, what I'm going to do here is I'm going to put a N in front of the S here. I'll explain why that N is sitting there. N in front of the P as well. An N minus 1 in front of the B, and an N minus 2 in front of the FE. Now, if we look at it, how many electrons can fit in the S sublevel in total? 2, right? There's 1, 2 families within that block. For the P's, well, it can hold a maximum of 6. There's 1, 2, 3, 4, 5, 6. You don't believe me? Count the periodic table. In the D block, if you count the number of families in the D block, there have to be 10. How many electrons they can hold? And in the F block, there happens to be 14. So once again, unbeknownst to Dmitri Mendeleev, he didn't know about it, but once again, the quantum mechanical model is just kind of fitting right in here. Also, one of the things that we know is there's like 7 energy levels out there. And if you look at the number of periods on the periodic table, N equals 1, N equals 2, N equals 3, N equals 4, N equals 5, N equals 6, and N is equal to 7. And at this moment, we are now ready to use this periodic table to write the electron configuration for any element. All I gotta do is kind of show you how we're gonna go about doing this. All right, here we go. So what we're gonna start off with is we're gonna start off with hydrogen here. We write its electron configuration, and then we'll continue to just move on until we feel really comfortable with using this periodic table. So if we look at hydrogen, hydrogen is going to sit right here. So hydrogen sits right here. The way that we read the periodic table is just like a book. We always start at the beginning on the far left in this case. So if I look at it, I'm in the first energy level, I'm in the S block, and that's why I have the N here, because that's really just, the N is 1, so 1s, and that's what we write down. 1s. And then within the family, I'm going to say, oh, it's just the first column of the family. Hence, I'm going to go with 1s, 1. If we look at helium, helium is the only element you got to be careful with. When you think of helium, it looks like it's a part of the P block. All the rest of the elements fall in the right block. But helium is really supposed to be right here. That's the only way you have to be careful of. Which means that when it comes to helium, we're still going to say, okay, it's in the 1, first energy level, it's in the S block, and then within the family, it's 1, 2, so I'm going to go 1s2. Gotcha. What we're going to do is we are going to jump to the next element, which is going to be lithium, which sits right here. When I look at lithium, I've got to start all the way from the beginning. So it has its own story. So I don't just start at the second energy level. I got to go back to the beginning here. And the beginning simply says, hey, I've got to go through the 1s. And then think about it. If I want to get to the 2s, that means the 1s has to be completely filled. You have choices here. You can go in and simply say 1s, and then count the number 1, 2, I'm out the family. Or you just say the S is completely filled. I know to be completely filled, it needs 2 electrons, 1s2. And then I'm going to the second energy level, and it's going to be 2s. And once again, it's in the first column, so 2s1. There goes my electron configuration. Let's jump down here a little bit. We got boron, carbon, nitrogen, and we'll go with nitrogen, that's fine. The electron configuration for nitrogen here. Starting all the way back at the beginning. So I'm going to go 1s. I got to come up the 1s, it's completely filled. I'll put it in 2 here. I'm going across the periodic table. I need to go all the way over here to the second 2p's. So if I'm going through the 2s coming out of it, that's full. So I'm just writing 2s2 right here. And then I'm going to go 2p, because that's where I'm at. I'm over in still the second energy level, still that second period here. 2p, I'm going to go 1, 2, 3, 2p3. I'm done. Yes.
Wait, so for lithium, why did you put 1s squared in it?
1s2?
Or yeah, 1s squared.
Because remember, in order to get to the story of lithium, I first have to start at the beginning of the book. And the beginning of the book is always starting at the beginning. We got to tell where all its lower line electrons happen to be, because lithium has a grand total of 3 electrons. The first 2 electrons are the 1s. And once again, it's completely full, so it's 1s2. And then it's just 2s1 in this case.
So like if you went all the way down to like...
Oh, no, we're going to go there.
Okay.
We're going to go further and further into this thing. Matter of fact, let's do this. Let's go, we'll go again across the 3rd energy level. This needs to actually draw just a little bit further down, like that. And then we'll go all the way up to, let's try sulfur. Now, you might need a periodic table, so you can count how many columns happen to sit there, or better yet, why don't I do this? See if I can check this up here, the periodic table. There we go. So I'm going to erase my periodic table I have up here. And I'll kind of recreate it, but write the numbers. There we go, the division of the blocks. We said this was the N of S. N of P block, N minus 1 of D, which we haven't gotten to yet. But if we look at it, if we go all the way to sulfur, writing the electron configuration, remember it goes N equals 1, N equals 2, N equals 3, N equals 4, N equals 5, N equals 6, and N is equal to 7. So if we look at sulfur, and we wanted to write the electron configuration for sulfur in this case, then what we do is we do something like this right here. Go all the way back to the beginning. 1s, okay, well I have come out of the 1s, so I'm going to say that's completely full, so 1s2. Next, I'm going through the 2s. Well, that's completely full because I got to get to the 2p's. Okay, that means this has to be 2s2. The next thing is I'm going through the 2p's and I'm coming out of it. Okay, that means if I went all the way through it, it's got to be completely filled, so that's 2p6. Then I'm going 3s, came out of it, so that's 3s2. And then the last part is now going to the 3p, and we want it sulfur 1, 2, 3, 4. So 3p, 4. What I want you to do now is I want you to write the electron configuration for carbon. Not carbon, I'm sorry, but calcium. Use the periodic table, see if you can write it. Calcium city right here. All right, so we finished. All right, and if you did it correctly, it should look just like this right here. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Because once again, it's telling the periodic table that 4s should come before the actual 3d. Now watch what's going to happen here. As we start to go into things such as maybe iron, and I ask you to write the electron configuration for iron, just realize that n minus 1 is a correction. This is not the 4D sublevel. It's the 3D sublevel, because that's what's sitting right there waiting for the next pair of electrons that are going in there in this case. That's why whenever you go through the D block, the correction is n minus 1. So what I want you to do is try writing the electron configuration in this case for iron. All right. Somebody help me out. Who wants to give me the electron configuration for iron? Anybody? Ellie, who you got for me?
1s2, and 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6.
Very good. Now watch what's going to happen here. Eventually, when we have a test of this material, I'm going to ask you for an orbital diagram. Before you write the orbital diagram, what you are going to do is you are going to write the electron configuration. Because the electron configuration is going to show you where all the different overlaps are going to take place. And then the next thing you're going to do is you're going to build your orbital diagram based upon the electron configuration. And watch how I'm going to do this. I'm going to say, okay, I got a 1s. The 1s has how many electrons? 1, 2. Next, I got my 2s, which is going to sit higher energy. How many electrons? 1, 2. I got my 2p. 1, 2, 3. It's got 6. 1, 2, 3, 4, 5, 6. I got my 3s. 1, 2. I got my 3p. 1, 2, 3. It's got 6. 1, 2, 3, 4, 5, 6. I got my 4s, which has 2. 1, 2. And then I got 1, 2, 3, 4, 5. My 3d, and it's got a grand total of 1, 2, 3, 4, 5, plus 1 more, which gives me my 6. And then the only thing I gotta do now is just go in here and say n equals 1. Who has a 1? Oh, you got a 1, I'll connect you. N equals 2. Who has a 2? Oh, you two are the only 2s here, I'll connect you. N equals 3. Okay, you're a 3, you're a 3. Oh, you're a 3 way up here. N equals 4, and I can see the overlapping that's actually taking place. Write the electron configuration and use it to build your orbital diagram. Now, worst case scenario when it comes to electron configurations in this class is I could ask you to write the electron configuration for barium. So why not go ahead and write it? That's worst case scenario on the test. That's as far as I will take you out. Even for the AP students, that's as far as they need to go as well. So you can write it there, you can write it for anything. All right, here we go. Barium. Who would like to provide me with the electron configuration for barium? Barium. Thank you. What do you got for me?
1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6x2.
Whoa, slow down.
Stop.
Okay, Logie.
4d10,
4d10. Okay, 4d10.
5p6,
5p6,
and 6x2.
6s2. Very nicely done. Any questions here? All right, so let me explain what you're going to do as your homework.